All right, so I'm going to skip Schwarz's treatment of the Casimir effect. I thought it was I have a treatment in my book, but on the other hand, in the book it's an example of complex variable theory. All right, I think I'll tell you qualitatively what's going on. Basically, if you have two plates, then there are boundary conditions. If you imagine the plates are perfectly conducting, then you have boundary conditions on the plates. And let me remind you what they are. I put these pages from my book, by the way, on the web page so you can read them. But I read them over last night and this afternoon, and I found that they were, it would take the whole hour and 15 minutes to go through just the Casimir effect, and I don't think we should do that. So let me just give you the thing qualitatively. Well, first I'll tell you, I mean, if you want to look at these pages, let me first of all say that there's something called the Abel-Plana formula, and this is something that is proven then as an example of complex variable theory in my book, and it's a half n1 plus a sum n equals n1 plus 1 to n2 minus 1 some f of n plus a half f of n2 minus the approximation, a continuous approximation to this. That this is equal to I integral 0 to infinity f n1 plus iy minus f n1 minus iy minus f n2 plus iy plus f n2 minus iy, all this divided by e to the 2 pi y minus 1 dy, and okay, and the assumptions here on f are that f is analytic, f of z is analytic, and bounded. So f of z less than or equal to some h, where h stands for huge. It's analytic and bounded for n1 less than or equal to real part of z less than or equal to n2. Okay, so if we make these two assumptions, notice we have analyticity, the bounds are on the real part of z. So we have some region between n1 and n2, it's analytic and bounded. Then you have this result. Obviously this integral is dramatically convergent because of the e to the 2 pi y for large y. The small y, there's a cancellation because f set y equal to 0, f of n1 minus f of n1, and so that's 0. So the singularity at 0 goes away. Anyway, that's the Abel-Plana formula, and one can find it in Whittaker and Watson. Which, by the way, is quite an elegant book. Some of these books that, in other words, this sort of, these, the stuff in my book, the first half of my book, was a field of study that many very bright people, very well-educated people, worked on in the early part of the 20th century. Wrote some marvelous books. Whitaker and Watson is one of them. Okay, so the rest of the Casimir effect is to say this. We've got these two plates, and there are boundary conditions that the electromagnetic field will satisfy on these plates, and let me say what it is, namely E tangential is going to be 0, and B normal is going to be 0 on the surface of the plates. And moreover, we can imagine that we put the whole universe in a huge cube, also bounded by metal that is perfectly conducting and satisfies these boundary conditions. Where we get the funding for that, I don't know. But let us just assume that. Then the next thing is to say that what are the modes in here? If this distance here is L, then the modes that are allowed are omega, k perp, and n. K perp means the wave number in that direction. This thing is c square root of k perp squared plus pi n over L squared. So if these are the frequencies, then we have, these are the, in other words, the k in the direction between the two modes is restricted by these conditions so as to give us E E. This E is 0 and that B is 0. And we're also assuming, if one talks about a metal plate that's a very good conductor, then this is 1 minus some omega plasma squared over omega squared times 1 minus I over omega tau. Here, tau is the mean time between electron collisions. Omega p is the plasma frequency of the metal, and this is basically, what this means then is that as omega goes to infinity, the thing becomes, epsilon goes to 1, and the metal becomes transparent. And so what we're going to say is that well, let me go over here. The energy then between the plates, which is basically an integral of E squared plus B squared over, I don't know, 8 pi or 2 or 4, whatever it is in the units you have. Anyway, in these units, it's pi h bar c over L, integral 0 to infinity, k perp dk perp over 2 pi, and now we have these square brackets, sum n equals 0 to infinity, square root of L squared, k perp squared, over pi squared plus n squared minus integral 0 to infinity, square root of L squared, k perp squared, over pi squared plus x squared dx minus L k perp over 2 pi. Okay, this is the difference in the energy due to the plates. The energy, in other words, this is the energy between the plates. This is the energy if the plates weren't there. And so this is the change in the energy due to the plates. And we can see how that varies with with L. And what one can do is introduce a cutoff which reflects this behavior of epsilon of omega. And which you choose, well, you don't really know what to choose. I'm going to have 1 plus n over n plasma to the minus 4. So 1 over that to the 4th power, effectively. N plasma is omega plasma L over pi c. And moreover, something that I probably should have said in the book but didn't is I'm going to assume that when we get to C of m, I'm going to set that equal to 0, where m is some m much greater than n plasma. So in other words, that one is going to be actually 0. Well, then if you rescale your variables, you get pi squared h bar c over 2L cubed, integral 0 to infinity p dp. And now we have this sum up to n c sub n root p squared plus n squared minus integral from 0 to m c of x square root of p squared plus x squared dx, and then minus p over 2. And now the point is that we've got this function f of z, which I'm calling c of z square root of p squared plus z squared. This thing, because of my choice, we could have had, I mean, this obviously isn't correct, but it's, you know, plausible, and then 0 beyond m. This thing is then square root of p squared plus z squared over 1 plus z over np to the 4th. Okay, this satisfies the conditions of being analytic. Well, it's actually analytic for the real part of z positive, and moreover, it's also bounded because we've got a z bounded at least for real part of z positive. So everything is hunky-dory. We can apply the Abel-Plana formula, and then this turns out to be pi squared h bar c over 2L cubed. I'm going to set c of m equal to 0 explicitly. PDP, and what we then have is I integral 0 to infinity c of iy square root of p squared plus epsilon plus iy squared minus, so these are these crazy terms that appear in the Abel-Plana formula, minus iy square root of p squared plus epsilon minus iy squared minus c m plus iy square root of p squared plus m plus I y squared, and then plus c of m minus iy square root of p squared plus m minus iy squared. All right, all of that dy, and then over e to the 2 pi y minus 1. And of course that exponential makes things make things converge. And what we do now is we also are neglecting these terms, which are C of M, C of M, and if you look at the nature of the potential, you see these integrals are going to be ignorable, and so we only have this. And if you, let me just skip ahead. If you do the arithmetic, what you find out is, and it's all, the pages are on, the details are online here. You get minus pi squared h bar c over L cubed, integral 0 to y, PdP, integral 0 to infinity, square root of y squared minus p squared e to the 2 pi y minus 1 dy, and that turns out to be minus pi squared h bar c over 3L cubed, integral 0 to infinity, y cubed dy over e to the 2 pi y minus 1. And then, miraculously enough, this turns out to be a Bernoulli number. There's a Bernoulli number in here. And so this is actually minus pi squared h bar c b2 over 3L cubed 8, which is minus pi squared h bar c over 720 L cubed. And as a result, the pressure between the plates, minus 1 over A, pushing the plates together, partial E of L, partial L, is equal to minus pi squared h bar c over 240 L to the 4th. And so that's what was predicted by Casimir back in, I think it was 1924. I don't have that in my notes now. But it wasn't observed until I think it was 1997 that it was finally observed and measured to be roughly this, approximately, or maybe very precisely, this result. One of the things that's always bothered me about this calculation, though, apart from some obvious things, is that, you know, if you forget about the electromagnetic field and you just have two plates, well, the atoms in the plates attract each other. And I remember talking with an expert on this subject about this, and he said, well, you can either look at it as the atoms in the plates, or you can look at it this way. And I said to him, well, why don't you just add the two effects and you get something twice as big? And he said, no, you're not supposed to do that. So I don't know. I am just a bit puzzled by this whole thing. Anyway, this is the best calculation I know of the Casimir effect. There may be something better, but as far as I know, this is about the best. Okay, let's now start renormalization in quantum field theory, or continue it. Let's think, first of all, and I'm going to be following Schwartz here. 5 box phi minus lambda over 4 factorial 5 to the 4th. Okay, so this is very much like the Higgs theory that Roosberg was talking about earlier. The difference is that we haven't put in a mass term at all. If we were talking about the neutral component of the Higgs, the part that was actually found in 2012 at CERN, we put in a plus mu squared phi squared here. after symmetry breaking. In other words, mu squared would have the wrong term. Remember, the action density is kinetic minus potential energy. Okay, so what are the diagrams if we're, say, doing scatter? Well, the lowest order is from this vertex here, and it's this Feynman diagram, and the value, which is minus I lambda. Then the first order correction, if we ignore T and U and just look at the S channel, this thing is, that's the diagram, and we can imagine that P is here, K, P minus K, although, actually I forgot, we also have a P prime here, and so this is actually, I think I'd have to add plus P prime, like that, and then we'd have, well, P double prime, P triple prime in general. Anyway, this is, so this is just, I'm just being, or as you see those dots. The point is, this would be a propagator, which would be 1 over k squared. This would be 1 over k squared. We're integrating k to the fourth. So this thing is proportional to integral d4 k over k to the fourth. And this thing is proportional to log of some lambda squared over, I don't know, some mass parameter m squared. Well, the mass is 0 here. Just pull in some parameter. In other words, it's logarithmically divergent. This is a logarithmically divergent integral. And on the other hand, if you actually get serious and do the integrals, and I'm going to, I think there are some equations here that might, I don't know, I found them somewhat sloppy. And so I'm going to skip them and just come to the actual answer. If you do the thing carefully, what you find out is that M2S is equal to minus lambda squared over 32 pi squared log S over lambda squared, where lambda is some ultra-bias cutoff. Okay. By the way, this is by no means the worst singularity in this theory. If we had instead been talking about the diagram in which the lowest order term is that, and then we have the correction, a correction like that, well, that actually is a log also, now that I think about it. But there's another term, which is this term. So that's just a log, but this is quadratically divergent because it's d4 k over a single propagator. And this is one of the ones Roosevelt was talking about. So that's why, that's the worst singularity apart from, of course, the vacuum energies. Now, this is bad, but because it's only a log, it's not terribly bad. In other words, m of s1 minus m of s2, this is just lambda squared over 32 pi squared log of s2 over s1. So the difference of the two is finite. And of course, I mean, the reality here is that we don't know what the physics is at very short distances. We don't know if the particles are extended objects in space or extended objects in space-time. We don't know, we really don't know what's going on. In fact, it just occurred to me that we always suppose that we should talk about particles, and in fact, you know, maybe we should just talk about processes. And if we just talk about processes, well, then you know, then the question would be, what's the fundamental process? And now we no longer are focusing on an object, but on a process. I don't know if that helps.
So there's going to be a talk by a
What?
mathematician philosopher on Friday exactly about this.
Yeah, I did read the abstract of his talk. I didn't actually
He's saying
go.
the same kind of thing.
I see. Yeah, well, it's thank you for bringing that up. I have to give you a tangent to that. Did you go to the talk?
It's on this next Friday.
It's what?
It's Friday this week.
Oh, it's this Friday.
Yeah.
I see. What time is it?
2 o'clock, I think.
2 o'clock?
But it's somewhere up in the.
Yeah, the trouble is we have an important visitor this Friday, and I don't know. Anyway,
If I can go, then I'll report back.
yeah, report back and give us the 2 or 3 sentences that are actually meaningful.
Yeah.
I'm very suspicious
Yeah,
of
so
philosophy.
We'll see.
It's not as bad as theology, but it's only one step removed. Okay, so cut out the jokes. All right, well, one of the key ideas in developing, in dealing with this problem of our ignorance of what's going on in very small scales is to try to formulate the theory in terms of things we can measure at macroscopic scales. And so then the idea is we define lambda r as the cross-section, and in fact, for some reason, it's minus the cross-section at some, or the amplitude, I should say, at some particular energy, or energy squared, S0. And if we compute this, then this will be lambda plus lambda squared over 32 pi squared log S0 over lambda squared. There will be all sorts of other terms. And so we're saying, well, these two things are finite. And if we're expressing them this way, then presumably lambda has to be infinite in order to compensate for that infinity. In any event, we can rewrite this thing as lambda is, or we can expand this is the parameter in the Lagrangian. So out of the Lagrangian is this parameter lambda. And we can say that it's some sort of a power series in the finite lambda, and that makes sense because this could be a divergent power series. Okay, well, we can rewrite this thing as lambda r. Oh my goodness, yeah, what was something? Yes, we're going to rewrite this equation. Lambda r equals, and now we're going to substitute for lambda r plus this series. So we've got here lambda r plus a lambda r squared plus dot dot dot. That's this term. Plus lambda r plus a lambda r squared plus dot dot dot. 32 pi squared log S0 over lambda squared. Okay. So that's this formula on the right-hand side here. And so simplifying it a little bit, this is lambda r is lambda r plus a lambda r squared plus lambda r squared over 32 pi squared log S0 over lambda squared, and then dot, dot, dot. Well, that means that we know what A is. Namely, A had better be minus 1 over 32 pi squared log S0 over lambda squared. In that case, we can say here that this expression is lambda r minus lambda r squared over 32 pi squared log S0 over lambda squared. Okay. And then we have our expression for ms. Well, we just replace S0 by S, and we have m of s is minus lambda squared over 32 pi squared log s over lambda squared. Well, this is just what we would get from the original Lagrangian going in one loop and putting in a cutoff. But now we're going to write lambda like this. And so this is minus lambda r minus lambda r squared. Lambda r meaning the finite one. So here we've just used the equation that lambda is lambda r plus lambda r squared plus dot dot dot, ignoring the dot 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 and working only to order lambda r squared. So we have that expression there. Okay, now there's a typo in the book, by the way, and I've corrected it here. So this is then minus lambda r squared over 32 pi squared. And then the remarkable thing is that these terms cancel. And so then one has log s over s0. Okay, so that means that we've expressed the scattering amplitude and arbitrary s in terms of lambda r, which is the scattering minus the scattering amplitude at S0, and then a log term that expresses represents the difference, the change in the amplitude as you go from S0 to S. And so that's a nice formula, and that's the spirit of renormalization, that you express your observables in terms of your observables and different energies or different physical parameters. Of course, we still don't know what's going on in short distances, but we've rewritten things in such a way that we've expressed the finite observables in terms of finite parameters and other finite observables. And that's, of course, the goal. I mean, it'd be nice to know what's going on at very, very short distances. But since we don't, I mean, at the moment we don't know. Well, there are people who think they know, and they may be right. One of the things that's appealing about string theory is that it's a serious attempt to deal with the problem of infinities rather than just basically hiding them, which is what we're doing here. Let me swing over here once again and remind you that in this original Lagrangian then, this term is imagined to be some unmeasurable infinite quantity. thing that, by the way, we've done here, this is very closely related to what's called the renormalization group. As far as I know, it's not a group, and at least I've never understood why it might be a group. But maybe it's a group of transformations. Anyway, the renormalization group is something that's it's close to what we're doing here. Let me just get a drink of tea or water or something, and then I'll go on. Any questions?
Can you explain again the first line?
What?
Can you explain the first line again?
What's this?
Why do we have this equality?
Why what?
Why do we have this equality? Lambda r is, you just define.
Oh, we're going to define
a new
lambda r. Well, first of all, let's go back here. If we cancel out an I, then the lowest order tree level amplitude is just minus lambda. Okay. So the idea is that great question, because the idea here then is that we're going to define the renormalized coupling constant, the finite one, as minus the physical amplitude at some energy scale. And what does that mean? That means that once we've written the theory in terms of lambda r, the tree level approximation is exact at S0. Exact at S0. And so this then is effectively a running, in the trade we call it a running coupling constant. I don't know why it's running rather than walking or crawling. Or flying, but anyway, it's a running coupling constant, and what that means is that at a different energy S, you have a different lambda. But whatever it is, lambda, this running lambda is is something that should be the, if you let it run, then it's the amplitude at S0. At S, if it's running. Okay. And you can, later I'm sure we'll be computing that. Right now, let me give you the more traditional approach. The more traditional approach is to rewrite this original Lagrangian action density as we're going to write it in terms of lambda r over 4 factorial. Well, there's a typo in my notes. And then we're going to write this as delta lambda over 4 factorial 5e4. So in other words, lambda is lambda r plus delta lambda. But of course, this delta lambda is going to be infinite. Okay. So, what do we do? Well, if we now use this action density to compute the S-channel amplitude, we get minus lambda r minus delta lambda minus lambda r, and literally it would be lambda r plus delta lambda squared over 32 pi squared log S over lambda squared. But, and so that's what we would have literally. So what we do is we're going to set delta lambda equal to minus lambda r squared over 32 pi squared But we can't, of course, set something that's a constant equal to something that's a function of s. So we're going to set this equal to lambda s0 over lambda squared. And now when we do that, there's sort of a fudge here, and unless I've made some mistake or Schwartz has made some mistake. Yeah, you know, I think if you're going to make this work, well, I mean, there are two ways of proceeding. The way that Schwartz went was he said, well, this delta lambda, although it's infinite, it's a power series in lambda r. And in fact, if you treat it as a power series in lambda r, this is the part that's just dreadful, I think, because you're saying that it's infinite, but it's a power series in lambda r, and we're going to neglect it here compared to lambda r. But it's infinite. How can we neglect it in terms of lambda r? I mean, this is really, you know, I mean, this is what people say about North Korea. I don't know. But I don't think North Korea is at all as bad as this. All right. Anyway, if we do ignore this here as being higher order in lambda, and in fact we set delta lambda equal to minus lambda r squared times that. If we do that, then what's going to happen is that this term is going to combine with that term, and what we're going to have then is the same result as what we had before, which is minus lambda r squared over 32 pi squared log s over s0. So basically, I think the first procedure made a lot more sense than this procedure. Okay, and of course it's still true that m of s0 is minus lambda r. All right, the next step is to do this a little bit more accurately. So far we've been talking qualitatively, and we've just assumed that the Feynman integrals is something we can do, but we didn't actually do them. Now we're going to go to a simpler theory and do the Feynman integrals, and in fact use one of Feynman's tricks. Feynman was one of the many nice things about Feynman is that he was not pretentious, and he called things, I think, always by their simplest possible name, which is, of course, the right way to proceed. Let me get a piece of chalk that I can write with a little bit better. And I think we should end 5 minutes early because I've got to get to the polls before 7 in order to vote. There's a school board election, and I have to vote against the one who thinks the world is 6,000 years old. Or less. Okay, all right, so the simpler theory has an action density of minus a half pi, and now we're going to put the mass back in. actually, would somebody look in the book, is there actually a plus sign here?
Here's a plus sign.
Plus sign, all right. Now, you might say, why is the plus sign, isn't that the wrong sign? Well, the fact is this theory is nuts. Because this theory is saying that the potential is a cube of the field. So the field can assume, if it assumes just large positive values this way, it's unbounded below. If you put the minus sign here, you'd have, if the field assumes large negative values, it's unbounded below. In either case, it's unbounded below, so it's terrible. Anyway.
Is there any meaning to the cube potential?
Any meaning?
Yeah.
Oh, this is just something to illustrate how one would, if this theory were true, how one would deal with it. So we're just going to ignore that. Okay. So let's look at IM loop of P. What's that? Well, it's this particle going along. Actually, all right, P, K, P minus K, P. And we're even going to imagine that P squared is not necessarily equal to M squared. In other words, we're going to have basically arbitrary P, four vector P. We integrate over all of 4 vectors K. And now what we've got is 1/2 IG squared integral d4 K over 2 pi to the 4th I over P minus K squared minus M squared plus I epsilon I over K squared minus M squared plus I epsilon. And of course I'm following Schwartz here, so I'm using his metric, which instead of Weinberg's. Okay. Now, Feynman called one of his many identities a trick. And the trick is that 1 over AB is integral 0 to 1 over A plus B minus A x squared dx. And I see someone looking at it curiously, suspiciously, so let me show you how this actually works. This is an integral over x, so it's one we can do analytically. So it's 1 over b minus a, 1 over a plus b minus a, x 0 to 1. And now this is minus 1 over b minus a, 1 over b minus 1 over a. And so this is minus 1 over b minus a times a minus b over ab. And indeed, this is 1 over ab. So that's one of Feynman's tricks. You might imagine he's got another one. 1 over ABC is something analogous to that. And this is the first of a whole family of Feynman tricks. And in the old days, before computers, the easy part of one of these calculations was starting from the S matrix and arguing until you got to something like this. Okay. Then you had to employ the Feynman trick and do this integral. Okay. Well, it turns out that this integral after you put in A and B, and maybe you have the ABC case, this can actually be a hard integral. And in the old days, that meant something because you didn't have Mathematica or Intel and so forth, or Apple. The next thing, but still the x integral in the old days was still easier than the next step, because here we're doing phi cubed for simplicity so that we can talk about the concepts. But if we're talking about real life, then we have spin 1/2 matter particles and spin 1 gauge bosons. And the result is that you then have a trace. And last time I actually did one of those traces for Compton scattering, and you saw that it was non-trivial. Of course, there are computer programs for doing that, but I thought it was easier just to do it than to actually use the program, because I couldn't find the program. I imagine though, if somebody uses CERN Live routinely, that one can find a good program to do these things. Okay, anyway, what do we do? Well, we're running out of board space, so I'm going to set A equal to P minus K squared minus M squared plus I epsilon. B equal to K squared minus M squared plus I epsilon. Okay. All right, now the way I did it differently from what Schwartz did. And, maybe his way is the simplest. I don't know. I couldn't figure out what he was doing, so I did it this way. So what we want is A plus B minus AX. Well, what is that? Well, that's certainly B minus K squared minus M squared plus I epsilon plus B minus A. Well, B minus A, this part cancels, so it's K squared minus P minus K squared. Okay, so that's the Feynman denominator, but we have to square this, remember. So we work this out, and it's P squared minus 2pk plus K squared minus M squared plus I epsilon plus 2pk minus P squared times X. Or equivalently, P squared times 1 minus X minus 2pk times 1 minus X plus K squared minus M squared plus I epsilon. Okay. What we want to do is we want to shift K, and actually I should say that the right way to do this is not to shift K now. The right way to do this is first make this a finite integral, then shift K. Okay. It turns out that in this particular case, the two things commute, but I think the right way to do it is actually to first regulate this infinity. And the regulation that we're going to use is an old regulation invented by Pauli and Villars, who was a professor at MIT for a long time. Presumably, I don't know, my graduate student or postdoc of Pauli's. Anyway, but if for simplicity we just proceed this way, then what I want to do is arrange things. Here we have a K squared, a linear term in K. We want to make this, we want to shift so that we have something K squared plus beta. And we're going to take this whole thing and shift K. So what we do is we have here K plus alpha squared, that's this term. Then this term is minus 2p k plus alpha times, well, sorry, we're dealing with this, times 1 minus x. So I've shifted k here and here, and then we have the other terms, which are p squared times 1 minus x minus m squared plus I epsilon, and that's going to be beta. Well, we want to get rid of the linear term in k, and so that means that we set alpha equal to p 1 minus x. And that way we have 2k alpha here, and then over here we have minus 2p 1 minus xk. So if alpha is p1 minus x, then the linear term cancels. And beta, which is everything else, turns out to be p times 1 minus x squared minus 2p 1 minus x squared, which is also known as minus this. So that's what it turns out to be. And then this denominator then is 1/2 ig squared integral d4 k over 2 pi to the 4th. Okay, hold on, I've got to get everything straight here. Well, there are 2 i's here, and there's 2 i's there. So altogether, this is just g squared over 2. Then d4 k over 2 pi to the 4th, integral 0 to 1 dx, and then what's left? What's left is k squared minus m squared plus I epsilon plus x 1 minus x p squared squared. All right, so that's the logarithmically divergent integral. The part that we, now how do we regulate this? We regulate this by this Pauli-Villars thing, and basically it's if you have a propagator that's going like this, in other words, you have a d4 k, you have 1 over k squared minus m squared. Well, this is sort of doing it the nicest possible way. You say, well, there's this crazy thing going on here, minus delta squared. So you do that. Okay. And when you do that, that's a mathematical trick, but it's sort of doing the least harm. It's better than just a sharp cutoff at lambda. And so what we can imagine is that we first do this before we shift that's the way we should do it. But in any event, all right, I'm out of Blackboard now. Maybe I'll go over there where there's, but I got to only go another 5 minutes because I gotta go both. All right, does anybody have a question? I'm sort of hoping that the questions the board will dry. That's the point of mine. By the way, this business is, I think renormalization is confusing and troubling, and so you shouldn't feel bad that you're confused or troubled.
Why did we need to shift k?
Why do we need to shift k? All right, hold on. Well, we need to shift K because let's look at it before K. Because we want to be able to do the d4 K integration. And if K is a complicated linear form, K dotted into P and everything, that's going to be that would be a nightmare. Thank you for the question. Okay, well, this Pauli the large thing is the idea. It's related to the ghosts that we introduced when we did the Faddeev-Popov trick. In other words, we're introducing a scalar particle with Fermi statistics, and then the propagator has the wrong overall sign. And so what we get is this extra term here, which is d4 K over 2 pi to the 4th, 1 over K squared minus delta plus I epsilon, and there's an I there, it comes in with a minus sign, and so altogether this is minus I over 16 pi squared delta over lambda squared. And so when one finally does this whole business, then putting these two things together, what we do is we set delta equal m squared minus p squared x, 1 minus x, and then altogether mi root of p is minus I g squared over 32 pi squared integral 0 to 1 dx log m squared minus p squared x 1 minus x over lambda squared. And doing the integral, it's g squared over 32 pi squared 2 minus log minus p squared over lambda squared. This is in the m equals 0 limit, just to make it a simpler calculation. And we're imagining that p squared is less than 0, which is a little bit bizarre, but we said p squared was all mass shell anyway. And this is, what we're going to be doing ultimately is we're going to be using this as a correction. In other words, if we have a theory that's like this, instead of having that, we can have, so this p does have p squared less than m squared in Bruce's notation, Schwartz's notation. So then we have, finally, ml of p is minus g squared 32 pi squared log q squared over lambda squared. So the idea is that we've got an amplitude now in terms of some infinite quantity and some q. So this is similar to what we had before, and well, we'll proceed from this next time. Let's stop now because, as I said, I've got to go vote for